This is an overview of the paper-controlled training data generation with diffusion models. A supervised model can give unreliable predictions when the target data distribution is different from its trained distribution. The target distribution can change over time, but training data usually stays fixed due to high collection costs. In this work, we use generative models and develop a controllable way of generating training data that adapts to a given target distribution and model. Text-to-image generative models can generate novel realistic images not seen during training in a controllable way. We use a generative model to generate training examples and to train a supervised model that performs well on a given target distribution. We describe later how we generate the data, X, that aligns with a given label, Y. Our goal is to develop a controllable way of generating training data that fits to a given model and target distribution. An open-loop approach generates training data using fixed handcrafted prompts. Open-loop approaches can result in generations that are not useful for training a given model. This example is not useful for training because the model classifies it correctly and has a low training loss on it. Open-loop approaches can also result in generations that are not relevant for a given target distribution. Note the differences in the generated image to the target distribution. For example, the target distribution has a lake in the background, is less saturated, zoomed out, etc. We introduce feedback mechanisms that automatically adapt the data generation process to a given model and target distribution. We make the prompt, or the token embeddings, similar to textual inversion, learnable. And condition the generation on the label, Y. We pass the generated image through the supervised model to make a prediction. And update the prompt by maximizing the model's loss. We call these prompts, adversarial prompts. Adversarial prompts result in images that fool the model but can be dissimilar to the target distribution. We therefore introduce another feedback mechanism to guide the generations towards a given target distribution. We use clip encoders to compare generated images with unlabeled target images and/or textual description of the target distribution. We call the method using only the guidance mechanism guided prompts. We can then combine feedbacks from both the model and target distribution to get guided adversarial prompts. Adversarial prompts generated an image of a zebra with buildings in the background. Although this fools a model, the target distribution are of zebras in the wild. Guided adversarial prompts generated an image of a zebra in a grassy field, which is relevant to the target distribution. Thus, guided adversarial prompts result in generations that fool the model and are relevant to the target distribution. We have seen how we can control the data generation process. Next, let's look at how we can generate aligned data for supervised training. An aligned example is an RGB image and its corresponding label. Let's look at some examples. For classification, we use the repaint in painting method to preserve the original object. Note that the blue region stays intact in the generated image. This gives us aligned data, that is, the RGB image corresponds to the object's class. For depth estimation, we use ControlNet with depth conditioning. We use the depth maps from the training dataset. We then use ControlNet to generate an RGB image conditioned on the given depth map. Note that the generated image has the same depth as the depth map we gave as input. Thus, this gives us aligned data for depth estimation. Adversarial prompts can attack the label conditioning instead of the model. In these examples, the generations do not follow the depth conditioning. We use early stopping and SD-edit to avoid collapse. SD-edit conditions the generative process on the original image and reduces its expressivity. For classification, the conditioning mechanism already ensures that the class label, object, stays intact. Now let's look at some results. We show promising results on the following tasks and datasets. Classification using Waterbirds and iWildCam datasets. and depth estimation using the taxonomy dataset. In this task, we aim to classify if a bird is a water bird or land bird. In the training distribution, the type of a bird is correlated with the background. And in the target distribution, bird is not correlated with the background. In this setting, if the optimization for guided adversarial prompts were successful, we would generate images of waterbirds on land and landbirds on water. Let's compare the generations from different prompts. Agnostic prompts are not informed of the model or the target distribution. Here, we use the prompt, nature. Next, we have adversarial prompts that fools the model but may not result in generations that are relevant to the target distribution. Guided prompts only takes into account the target distribution. Finally, guided adversarial prompts results in generations that fools the model and is relevant to the target distribution. Notice how guided adversarial prompt generates waterbirds on land and landbirds on water. Here are results from fine-tuning on the different generated data. Our results show that training with generated data from guided adversarial prompt results in the best performance. In this task, we aim to classify animals in camera trap photos. The training distribution consists of data from selected camera trap deployments. And the target distribution consists of data from new camera deployments. Some of the possible distribution shifts that can occur are changes in illumination, camera types, background, vegetation, color, and animal frequencies. Let's look at the generated data. We have agnostic prompts, from the prompt, camera trap. Adversarial prompts. Guided prompts. And guided adversarial prompts. Here are results from fine-tuning on the different generated data. Our results show that guided adversarial prompts again result in the best performance. We also show that GAP is data efficient, that is, it performs the best even with small amount of extra data. Finally, let's look at some results for depth estimation. The training distribution consists of indoor images from the taxonomy dataset. And the target distribution consists of data with shifts due to corruptions or from a new dataset. Let's look at the generated data. We have agnostic prompts, from the prompt, room. Adversarial prompts. Guided prompts. And guided adversarial prompts. Guided adversarial prompts generates fog that is more severe. Here are the generations for a different target distribution, blur. Here are results from fine-tuning on the different generated data. Our results show that guided adversarial prompts performs comparably or better compared to the baselines. See our paper for additional results, such as a comparison of the results from multiple iterations of adversarial optimization, generation, fine-tuning, versus a single iteration. We show that the latter is sufficient. We also show the results from performing adversarial optimization on different supervised models on the same task. And a visual and quantitative comparison of the generations from text and image guidance. To conclude, we propose a closed-loop method to generate training data that is useful for a given model and target distribution. Model-informed feedback generates adversarial examples. Target-informed feedback generates images close to the target distribution. We show positive results for different tasks, distribution shifts and models. Thanks for listening. Visit our website for more details.